In this lecture sequence, we will discuss the basics of Monte Carlo path tracing, which is the core algorithm that you will be implementing for indirect lighting in global illumination in CSE 168. Monte Carlo path tracing enables a general solution to rendering in global illumination. It is suitable for a variety of general scenes. It is based on Monte Carlo methods, which are randomized algorithms that seek to sample all paths of light transport in the scene. The advantages are that one can handle any type of geometry, whether it's procedural geometry, curved geometry, and so on, any type of reflectance function or BRDF. You can handle samples of all types of paths. In what I've written here, we use regular expression. L is from the light, S and D correspond to specular and diffuse, E corresponds to the eye. So you can have paths that go from the light, have any number of specular or diffuse bounces corresponding to the BRDFs that may be specular, glossy, or diffuse, and end up at the eye. The accuracy can be controlled at the pixel level simply by increasing the number of samples through each pixel. Monte Carlo path tracing also requires very minimal memory consumption. Each pixel is separate. It is an unbiased technique in the sense that error appears as noise in the final image. The disadvantages, which are standard Monte Carlo disadvantages, are slow convergence. The variance goes as 1 over the number of samples. The standard deviation or root mean square error goes as 1 over square root of the number of samples. And this is manifested most commonly as noise in the final image. The goal in Monte Carlo path tracing is to integrate the radiance for each pixel by sampling all paths of light from the light source to the viewer. For example, here is one path that goes from the light source, hits a specular surface, hits a diffuse surface, and then hits the eye. And this is a representation of the rendering equation, and we seek to consider all of the paths that the rendering equation encompasses. Here is a simple Monte Carlo ray tracer. You choose a particular ray per pixel. Notice that in this case, the ray can also go through any pixel location U and V through that pixel. You assign a weight equal to 1. You trace the ray to find the intersection with the nearest surface. At this surface, you randomly choose between sampling emission paths and sampling reflected paths. If you are sampling an emission path, then you stop the ray there because you're directly hitting the light source for the emission, and you return whatever the weight is at that point times the emissive value or the emissive radiance. If you're considering the reflected path, then the weight gets multiplied by the reflectance. You generate a ray in a random direction, and at this point essentially do recursive ray tracing. You go back and trace another ray. Some of the challenges we'll have to face is how do we generate random points or directions in path tracing, and most critically, how do you reduce variance? If you implement the algorithm on the previous slide, you will get extreme noise and require a huge number of samples. Of course, like in standard Monte Carlo integration we talked about, variance can be reduced by importance sampling, for example, sampling according to the BRDF, as well as stratified sampling. We'll now talk about the implementation of a simple path tracer, then we'll discuss variance reductions and some nuts and bolts of 2D sampling techniques. Here's the simple Monte Carlo path tracer. For each pixel separately, you cast n samples and average. You choose a ray with the origin being the camera and a direction corresponding to a location within the pixel. So you can pick a random location within the pixel. The pixel is a square. That will give you a particular direction that you can denote with theta and phi. The pixel color is simply 1 over n times the color obtained by tracing that path through the scene. Effectively, this is Monte Carlo integration. You're averaging or normalizing by the n samples you trace through that pixel. And error can be controlled simply by increasing the number of samples through the pixel. The trace path function returns an RGB value, a radiance value, and it calls itself recursively. So first it traces a ray from the point P, direction D, to find the nearest intersection P prime. This applies both to primary rays and secondary rays to handle interreflections and global illumination. Once it finds an intersection, let's say it selects with probability 50% going to the emitted and 50% the reflected. For the emitted, you return twice the emissive radiance. Notice that the probability of being emissive is 1/2. In order to find a proper unbiased estimator for Monte Carlo, you need to divide by this probability, and hence you multiply by a factor of 2. Similarly, you multiply by a factor of 2 in reflected. For the reflected component, you generate a ray in a random direction d prime, and then simply return the factor of 2 times the BRDF corresponding to the path you've now created at the surface point of interest. D corresponds to the direction of the ray outgoing towards the eye, or outgoing in some other direction. Remember, this can be a multi-bounce path. And d prime is the ray going out from that point that continues the path. So it's the direction corresponding to d and d prime, the cosine term, and the radiance input to the ray, which is obtained by calling trace path recursively. Once again, I emphasize that path tracing controls error in this very simple way. You cast n samples and average over the paths. I also want to emphasize that in Monte Carlo, you have to divide by the probability to get an unbiased estimator. That's why you have these factors of 2 on emitted and reflected. Finally, this is a recursive algorithm. One question is, when does it ever terminate? If trace path keeps calling itself, it terminates when it hits the emission part. At that point, it just returns because the path does not continue further. Here are some images from the Arnold renderer, courtesy of Marcus Fajardo. These are all beautiful images which are captured under a hemispherical dome light. They showcase the soft shadows. They showcase effects that you can do in path tracing that would be very hard to do in standard ray tracing or with OpenGL. Here are some beautiful images from UC Berkeley's CS283, the Advanced Graphics course, initially taught as CS294. This is about a decade ago. These images are courtesy of Daniel Ritchie, who is now a professor at Brown University, but at that time was an undergraduate student in the course, and his partner for the assignment, Lita Cho. You can see some very beautiful effects, such as the effects of smoke here, rendering in an environment map with lighting coming from all incident directions with reflective surfaces. Some advantages and disadvantages of Monte Carlo path tracing. The advantage is that we can handle general scenes, reflectance, and so on. By contrast, the standard recursive ray tracing that you did in homework 1 only handles mirrors. We can handle general and arbitrary BRDFs. This algorithm is unbiased in the limit that you throw tens of thousands or an infinite number of samples, it will converge to the correct result. But it is horribly inefficient. You sample emitted 50% of the time, even if emitted is equal to 0. You throw reflected rays in random directions, even if you have a mirror surface. If the light source is small, you're almost never going to actually end up hitting the light. So the goal in path tracing is to improve the efficiency without introducing bias. Much of the research in path tracing has been about variance reduction, using many of the methods discussed for Monte Carlo integration last week. Indeed, this has been the subject of much interest in computer graphics from the 1990s and continuing until the present day, and the remainder of this course essentially discusses ways in which we can reduce the variance in path tracing.